So the first thing that I want to do is we want to degree the camshaft. I don't know if any of you have ever degreed a cam. If you've built hot rod performance engines, you've obviously taken this and done this. But what we're going to do is we're going to take this piston stop right here. We're going to take the plug out. And we're going to put a piston stop down in there to where when I roll the engine around, the piston will hit it. And we're going to mark this. So we're going to put a degree wheel on here. Now what that's going to do is it's going to locate true top dead center. Be aware that as the piston rolls around for between 4 and 8 degrees, depending on the stroke and the rod length, that piston is not moving. It's stable. So I'm actually moving the crank, but the piston doesn't move. So since I'm moving the crank and the piston's not moving, I don't know where true top dead is. So if I put a piston stop in here and I roll the crank around one way and it hits it and I put a mark, I mark this, and then I roll the other way and it stops here, then halfway in between the two stops is top dead center. So if I do this, now we have true top dead center, and that's what we've got to obtain first. Once we obtain true top dead center, now we can go ahead and take care of it. I want to adjust the valves on the engine, and we want the valve clearance to be set correct on both of these valves before proceeding with this style test. Now, if we have a rocker arm, we're going to take into account the rocker arm ratio. Now, if I had a 1-to-1 rocker, it would be 1-to-1. In other words, if this center line from this is 1 inch and this center line to here would be 1 inch, that's 1-to-1. But very few rockers are 1-to-1. That means that if I open this, I'm going to amplify, or I'm going to open it further on this end from a leverage point. So in this case, I have a 0 or in the center, and I have 1 inch this way. I'd have 1.55 inches over this way. Now what that's going to do is it's going to make the valve open further. And a lot of times you can even get hot rod or performance rockers, and they have a greater offset. They move this hole, so the hole is over here, and then this gives me a longer ratio here so I still can contact the valve. And they offset the shaft holes. And it's what that will do is give me more valve opening. But in a regular car, in this car, we want to just know what the rocker ratio is. The rocker ratio is 1.55 is my ratio. So if I wanted to use a cam card at 50 thousandths lift, and that's at the lifter, I would have to take the 155 by 50 thousandths. That means I need to open the valve to 0.077. So I need a higher opening rate in order to obtain the correct opening and closing. So first we're going to do the intake at 77 thousandths. That's right here on my 0 point. It comes around. And then we're going to get a reading right here. And we got 27 after top dead center when the intake valve opens. And the intake valve closes at 28. And again, this is at 77 thousandths or 50 thousandths of lifter movement. Now on the exhaust, we're going to do the same thing. The exhaust opens at 21 before bottom dead center, and it closes at 18 before top dead center. Now what we want to do is we want to take these numbers and we want to build the style cam card like we saw. Now this would be where we're opening and closing. We can see we have no overlap up here, and we have very short opening rates on this particular cam. So if we had the intake is opening at 27 and closing at 28, and the exhaust is opening at 21 and the exhaust is closing at 18. And again, that's shown here, the 18 before bottom dead center on the exhaust, for instance, and the 21 before. Now again, this is at 50 thousandths of opening rate. So now I want to show you why they're doing this. So this is my cam lobe. This is the heel of the cam, or the base circle. Now, when I go up onto the nose, that's my highest opening. But as I come off of this bottom circle, or the base circle, I start to open. Now, this is a clearance ramp. And what that's going to do is that's going to take the valve clearance out. And it's going to start to open the valve, and it's going to start to move it, and it's going to move it slower, and then I'm going to accelerate it as I come up the flank. Now, this is a lot like an elevator. When you guys are in an elevator and this elevator starts to move, it moves slow and then it speeds up. And then before it comes to the floor, it slows down again and then it stops. Now, if you just went to a full acceleration, you'd put so much energy into the system that you could break something. So we want to move it very slowly and then speed it up. And then we want to speed it closed and then slow it down and slowly set it. Now I can open the valve faster than I can close it. And that would be what most cams are. They're asymmetric. I open them faster and I close them slower. If it's symmetric, I open it and close it at the same rates. But one thing you got to realize is I can't just come off this base circle and just flat open the valve. There's too much energy into the system. So I got to slowly open it, and that's this clearance ramp. So in order for all the cams to be compared equally, they came up with this idea that we have a 50 thousandths opening. That means I'm going to open the lifter up into the ramp up here, 50 thousandths, but that's a lot of valve movement. At 50 thousandths, I've already established flow. So now we're going to go in and we're going to take this engine, now we've degreed it, and we're going to do an idle in-cylinder compression waveform with this. Now here's my waveform, and we're going to mark it. As we've seen, we've got the cursors, and we're going to push our button, and then we're going to get the gridding up. Now the gridding, as we can see right here, this bottom dead center, this is top dead, bottom dead, top dead, bottom dead, top dead. So this is going to be my decompression, what we might call power, but we're not making power because we have the spark plug out, so this is decompression. This is the exhaust, the intake, and the compression. So we can look at the valve here. We can figure out where this valve is opening, and we can see where this is closing. And then we can get a better idea of where it is. So let's mark these. Now the exhaust is opening at roughly about 46 degrees, and that's before bottom dead center. The exhaust valve opening is at 21. Now this is vastly different on these two. So this would be like using a cam card with a 50 thousandths opening. Now we look at the intake valve, and it says that it's closing at 28, but we're at 54. Again, way different from what we've actually have here as far as a running idling engine. And the idling engine is the best place to take my cam timing. So let's look at why this is. So the industry standard is to measure the lifter movement at 50 thousandths. And that's so we get all the slack out of it, and we have something to compare to from cam card to cam card, so we can really get a really good indicator. If everyone used that, then you could see what the differences of the cam is. But the SAE standard says that I establish flow at 6 thousandths. Remember on the one cam card we looked at earlier, and I pointed out that it was at 6 thousandths. One reading is at 50 and one is at 6. Now what this shows me is I have 6 thousandths. Now this is where I establish flow. So basically, what I need to do is we need to redo that test with 6 thousandths. So now we did the same test where we roll it around and we find the valve opening at 6. Now we have something that the cam card looks way different, doesn't it? Like I have a lot longer opening rates on the cam. And this was taken off of this cam, actually degreeing the cam. And the intake valve opening is at 2 degrees after top dead center. The intake valve closing is at 59 after bottom dead center. The exhaust valve opening is at 57 degrees before bottom dead center, and the exhaust valve closing is at 4. So now we can see that this over here before bottom dead center is at 57, and I'm going to close the intake here. The intake closes at 59 after bottom dead center. Now let's go look at our car and let's see what we've got. So now this is taken at 6 thousandths of flow. Now when we come over and we see that we're at 54 and the intake valve closing is at 59, we're fairly close to that. Now, when we look at the exhaust at 46 and we look at the exhaust valve opening at 57, we're a little bit from that. Now I want to explain some of this. What this is 6 thousandths is where you start to have a flow change. In other words, if I open 6 or greater, I can have flow established. So at 6 thousandths, that's saying I can establish flow. But in order to change the pressure waveform, the in-cylinder pressure waveform, it isn't a matter of just establishing the flow. You have to have a volume change. So now we can understand that there has to be a volume change to change the pressure. So what I wanted to show you this is if you're looking at a cam card and you're comparing it to one of these waveforms, you may say these waveforms don't work. But is what you're not taking into account is where we're taking that cam card from. Is it at the 50 thousandths lifter opening, or is it the 6 thousandths lifter movement? Each one of these will be different. And they're also going to have to establish enough volume change within the cylinder before we actually see this change. So if the valve actually opened a little bit over here, at let's say 57, well, the problem is we didn't have a flow change. We have to have the air going back in from the exhaust system into the cylinder. That takes time. There's latency. So when I first open the valve to where I have enough flow to be established to change the volume, volume has to change in order to get a pressure change. So that's what's really happening. So just be aware that whenever you're looking at a cam card, you're going to have to not be at either number because there's some discrepancies of when the flow is going to be established and when the volume is going to be established. So that's just really important to understand that when you're looking at this. So what I've developed is rule of thumbs that give me the data that I need while I'm diagnosing cars. So first off, this exhaust ramp, this is the exhaust ramp. It needs to be bigger than 5 psi, which is 10 inches of mercury. If this only has 2 psi, I don't have enough differential to get a good ramp to where I'm going to measure halfway up the ramp or where this mark is falling through the waveform. Now right here, I can also see that the target down here for my valve opening, that's where I draw a line here and I draw a line here and I see clear place or a clear place I can see where the valve opened, a pressure change, a clear pressure change of opening. So at that point, I can start to see that that changed, and I want that to happen 30 to 50 degrees. And that's just a rule of thumb. Some cars are over at 60, but a good rule of thumb for most cars is going to be 30 to 60. I want that pocket to be made. Now, on the intake side, we want that to be 40 to 60. So 60, this is 30, 60. I want it to come across flat and rise, usually somewhere around 50 to 60, but 40. And again, some cars are 30. But the rule of thumb is 40 to 60. That gives me something that I can really use so I can see that if this is in a target plane or not, and if it's way off or not. So I'm going to use these targets. And again, we also want to use the ramps because this is the point where the valve is opening and closing, but we want to use the ramps as well. And again, we want to use the intake pulls and the exhaust pushes again, and I'll show you that shortly. And here we've got this measured where this is the zero plane, atmosphere, and we bottom from the bottom of the waveform, and we move a cursor halfway through. Now is what I can see is these ramps about halfway through. And I can see that this ramp right here is happening. That's 30. And this is a little higher. So we're actually not at 30. We're about 20 here. And that's going to be okay. And if we come over here and we see that about halfway up the ramp and where we really have the crossing is up towards the top. Now I want somewhere between the halfway and up into the ramp for this marker, bottom dead center mark, to come through. If it comes through down here at the bottom, it's telling me that I have a problem. If it comes through over here and right around in here, this is a good target. In other words, it's another place I get cam timing. I want to check the timing from when the valve opened, and I want to check my crossing point. Again, I want to check where my valve opened, where it started to have this drop, and then I want to check my crossing points, where did I cross, and my closing point. We always want multiple components to find this out. With a VVT system, I'm looking at 20 where it does not have cam timing, and I want 30 degrees after top dead if I have valve timing. So this is sort of the rule of thumb. So this target plane, I want the target plane to be halfway up the ramp into the top of the ramp. If it's way down here at the bottom and this whole ramp is to the right of my bottom dead center mark, that's retarded. If the whole ramp is over to the left, it's early and that's advanced. So if the marker falls here and the ramp is over here, it's advanced. If the target falls over here and the whole ramp is on the right-hand side, it's R&R. It's retarded or it's late. Now, the same is over here. If I have this marker and the whole thing is over here and it's to the right, it's retarded. If the whole ramp is to the left, this is my marker, and the whole ramp is to the left, it's advanced. So here's an idea to where if the bottom dead center mark and the whole ramp is to the right, it's retarded. If the opening is over here and the whole ramp happened over here, then I'm advanced. If the whole ramp is over on this side, this is my marker, top dead center. If the ramp falls on the right-hand side, it's retarded, R&R. If the whole ramp falls by the top dead center mark, like this, then we're advanced. So that gives you an idea of how we're going to use the markers across this. Now, the drive gear is the crank, and the driven gear is the cam. Now, if you count the teeth, the drive teeth on this, and divide them by the drive teeth of this, you're going to usually come up somewhere between 11 and 21 degrees. So I found that you do about 15 degrees per tooth as a rule of thumb. I've been doing all of these rules of thumbs for 15 years or so. So you need to understand that this really works because I do this every day. And so if I think that each tooth is worth about 15 degrees, it always gives me a good indication if I'm a full tooth off or I'm less than a full tooth off. And I have a real good indication that way. Now, this is my compression waveform right here, as we've already seen. And now we're going to have these pulls. And this is the intake pull. And these here are my exhaust pushes. So now we can overlay these waveforms and I can get a better idea. Now, as long as I'm using a regular pressure transducer, not a delta sensor, a pulse, I can actually see how much vacuum I had. And the vacuum is very important to me. In other words, I want to know where my vacuum is. If I've got 15 or 20 inches or I got 10 or 8, I want to know that. Now, when I zoom in on this, it's going to give me all the data that I need is in here. That looks like a flat line, but that line is not flat. During crank or running, I can see the pulls that are occurring in that, as I'll show you. The exhaust pushes again. This is atmosphere at 0, and I'm pushing the exhaust out. And this has higher is pressure and lower is vacuum. And we'll cover that here shortly. So here is my intake pulls, and I want to come across, and I can see where my intake here is falling. And what I want to do is we want to take the cursor and we want to mark the peaks, and then we want to mark my divisions or each cylinder. Now, if I go halfway, so I can see the marker 1, 2, right here, 2, 3, 4. And if I go 2 halfway, that's 1 crank revolution. If I go 1 crank revolution and I go to the right, this cylinder, this is my peak, these are my compression towers here. If I go to the right, this is the top dead center. The intake pull starts right here. Do you see how this actually came and it fell, and then I have this quick drop? Well, right there is where that intake valve opened, and I establish flow, and it drops. So this is telling me where I actually established the flow from that valve. When that valve, this is my pull, the piston was going down, and I pull more vacuum, and right here the valve opens, and I lose vacuum. Now, the piston starts to move down in the cylinder, and it pulls vacuum back up, and we get close to the top, and the piston stops moving as fast, and right here I open the valve and it drops. So the drop halfway is this cylinder's pull. So this pull, or this cylinder box, halfway, and then I go to the right, whatever cylinder I'm in, this pull belongs to this cylinder. So in this case, if I've got a peak and a peak, this is my compression tower, and this is my compression tower, I go halfway, and to the right is my intake pull. And you can see right here where the valve actually opened, and I get this rapid drop down. Now that's telling me where I opened, and then this is where I start to pull back up. The piston is moving until the piston almost comes to the top, and it's not moving enough volume. The piston is about to stop, and then this is the next valve opening, and I drop and I pull down. So this is the structure we're looking at for the intake pulls. In order to mark these intake pulls, if I was looking at the ignition timing, I would look at 1, 3, 4, 2, 1. Now, if I look at the intake pulls, this is my marker. So that's the halfway point. So now 1 goes to this. In other words, this tower from number 1 on my ignition fire, I'm going to take my ignition fire, and then I'm going to come halfway, and then this is the pull, and this is going to be my intake. So I'm going to take the firing order, 1, 3, 4, 2, 1, and now I'm going to put it over here, 1, 3, 4, 2, 1. And that's the way that this is going to work. So halfway, this is the pull for the cylinder. If I don't have a compression tower, but I had an ignition event happen, I can go ignition event to ignition event, and I can put a grid on this, and then I can figure out my pulls or my pushes for my exhaust. So this is the way that this is going to be accomplished. This is a 4-cylinder engine, so we have 4 cylinders. If we add more, we would just add cylinders in here, and we would put a 6 or an 8 or a 10 or whatever the cylinder is, and we would divide it, and then the pulls would be divided by the number of cylinders. These are the exhaust pushes. Now I want to put a point here to where I've got this marker, and we can see right here where we had a change. That pressure changed right there, and that's the marker that came up there. Now, this pull is going to be coming up, and this has got a deeper pull. It's getting vacuum here. And this vacuum from that miss is, remember, we didn't fire the fuel in this cylinder. The plug is out. So when that valve opens, the atmosphere here is rushing back into the tailpipe. So notice that when I open this up, there's some latency, and then we're taking volume out of the exhaust pipe, and the exhaust pipe drops its pressure. When I drop this pressure, this is going to show me how to find a misfire with the tailpipe exhaust. So when this valve opens, I have negative pressure or vacuum in here because I sealed it over here. This is vacuum. I sealed it, I compressed it, and then I decompressed it, and I opened the valve. This atmospheric pressure rushes in to the cylinder to fill it, and it changes the volume state in the exhaust, and now I can time when I get this drop in the exhaust with what cylinder created it. So here's a little bit better. So here we've got a push. This is higher pressure. This is lower. We pushed, and then we have this, and then we pushed. Now notice the valve opened right here, and this is a running idling engine. So there's more volume in the exhaust during an idle. Now as soon as we come up and we can see this drop right here, we get a big drop, This is a negative pressure, and you see how I have a fast rise and we overshot? Do you see how these are lower and this is higher? So I have a deeper pocket with a fast rise and an overshoot. This is the cylinder that missed. So in this case, I would go with my compression tower to compression tower, and what we want to do is we want to come down here and we want to mark them. So this is my firing order, 1, 3, 4, 2, 1. Now we come to the 360 point, and we already know that the exhaust valve opened. This is my exhaust. Remember, this is the decompression or the power. I compressed it, and then I decompressed that volume. I'm decompressing it. This is my decompression right here. Now, if I've got a vacuum, when I open the valve, the air from atmosphere is going to rush into the cylinder, and when that happens, I'm going to change the pressure in the exhaust, and if I've got a tailpipe sensor in there, I get this deep fall. And when I get this deep fall right here, that's how I'm going to target this. This is the 360 point. Go to the left, and that's the same cylinder as this one. So if I'm in 1 here, I'd go to the 360 point, and now I apply the firing order. 1, 3, 4, 2. 1, 3, 4, 2. So that's really just a firing order. So to do this on any engine, I go to the 360 point or halfway through my strokes. That's 1 revolution. That's the second crank revolution. It takes 2 crank revolutions to make the 4 strokes of a 4-stroke auto engine. So this guy right here is top dead center. If I go to the left, it's the exhaust, and if I go to the right, it's the intake. So that's the way we're going to do this. And when we're looking for the miss, we're looking for this drop, and now we understand that's because the air is rushing back into the cylinder, and it takes time to change. This is when I open the valve over here. So I open the valve over here, but we don't get a pressure change. There's latency because I took time to change that volume in the exhaust. But the exhaust will drop inside this box. Now on some engines that are pressurized, I've got a turbo on here, I might not have this type of a drop. I might actually have a pressure rise here. So most engines, this is what we're going to see. But if you have a pressurized system, be aware that I can have a different type of waveform depending on if the cylinder has pressure in it or not. Now is what we want to do is we want to come up and we want to put a cursor through the mark, and we want a timing event. Now if I look at the timing event right here, this is where the spark was commanded and the spark occurred. And then we can measure from here to here, and we can get the reading. And basically, that's 16 degrees. That's right up here. If I take the cursor and I mark, if I mark from peak to peak, and then I can take the cursors and I can move them anywhere on this grid. And wherever the distance between these cursors are is shown in this box and in this scope, that's 16 degrees. With the grid, you could also see it down here. If I measured from here to here, and this is 30, you can see that that's about halfway through that ramp, or about 15 degrees. A little bit more accurate way is with the cursors, and now we have 16 degrees at idle, and that would be normal, and that's okay. Now, if I'm looking at where I'm going to have a port fuel injection, so the port fuel injector sprays on the back of the valve, and that's going to happen during the exhaust plateau. So I want to open the injector up in this area, and I want the fuel stock to be sprayed on. That valve is closed, and I want that fuel to spray on that hot valve. And that fuel, that injector is aimed at that hot valve. It's not aimed at hitting the port. That fuel all goes to hit that valve. And when that fuel hits that valve is running between 400 and 800 degrees Fahrenheit. That means that the fuel's going to vaporize. It's going to take the heat on from that valve, and it's going to turn to a vapor. It also takes heat out of the valve so the valve doesn't run as hot. So in this case, this helps me to get the fuel changed from a liquid to a vapor, and then when the valve opens, I squirt that fuel right before I'm going to open the valve. Well, if I put the fuel on this exhaust side right over here, and I open the valve, so I spray the fuel, it hits the valve, and then the valve opens and I pull this in. So that's a timed event, and that is a timed event just like a spark plug. In a GDI engine where I spray this fuel into the chamber here, I'm going to have it on the induction cycle. So now I want the valve open. Usually I'm going to have it somewhere down here. Now on a GDI engine during crank, I might inject the fuel all the way over here between 30 to 60 degrees before my top dead center point. And that's normal. That is due to emission requirements. So I'm going to have better fuel atomization and burn characteristics if I'm cranking the engine and I have a late timing event. Not all cars do that. Hyundai and Kia don't, but most all the other cars during cranking, they fire the injector over in here. Once the car's running, I'm going to fire in here during my intake opening phase. Snap, throttle, and cylinder compression waveform. Here we go on this one. So basically, we're going to do snap. We've got 40 to 160. We've already looked at this. This is obviously relative. Always be aware of that. Now here's my intake pull right here. Do you see where when I open that throttle, the vacuum drops? This higher is vacuum, so 0, 20, so that's about 16 or so inches of vacuum that I have vacuum, and then I open the throttle and the vacuum drops. When the vacuum dropped, notice this plateau, this is made by vacuum. When the vacuum falls away, I no longer have the plateau. I have a very small pressure waveform, but there's no big plateau. So that's what we should have. This plateau is made by vacuum, as we've already covered. So if I lose the vacuum, I lose the plateau, and that's normal. And then we should have our drop here. So the exhaust plateau drops with a loss of vacuum, and this is what we see with the two sensors overlaying each other. Now here we have a ignition timing event of 24 that's happening at before top dead center, and when I snap it, I'm retarding the timing slightly to negate or mitigate a pre-ignition event. Pre-ignition is something where we don't want pre-ignition or detonation. Pre-ignition is where we fire early. Detonation is where I have a supersonic waveform that occurs. All of these pressure waveforms that occur in a cylinder are subsonic. A supersonic waveform will damage a motor. It'll damage the piston, put a hole in it, break the piston. It's something that's not wanted. So detonation is supersonic, where pre-ignition is subsonic, and all combustion phases, they're subsonic. So here we go. We've got this marked out here, and we want to look at my timing here. And so this is during a snap, and we can see my pockets, and we don't mark these out like this, okay? I just wanted to mark them to show you what you can see, but don't use these as cam timing because that's just not a good idea, but you need to see what happens. So this is my idle. I snapped it. I want to look up in here for any kind of a plugged exhaust. Now I want to come down here in the high vacuum, the decel area, and I want to look at that vacuum as well to see what it's doing. Now right away, I want this peak to be higher. So this is the peak from the pressure, and this is the exhaust. And these should always be higher. And you can see right here where they get really close, but then they start to separate. When these stay really low, it's indicative that I've got a problem with the engine. I'm not letting it in. So here we go, and we got this, and now we're under this ignition, and we can see decel. And what we had is, if we mark this, where we've got this firing to the peak, I have 140 degrees. Now we know that they're not going to fire an ignition 140 degrees in advance. So what's happening? When I have a loss of volume in the cylinder, this peak pressure moves to the right. When I have a volume loss in the cylinder, top dead center no longer is true top dead center. It drifts to the right, or it shows that it's going to be retarded. So a volume within the cylinder sets peak pressure. So if I don't have a good volume, I'm not going to have a good top dead center position. So we can see that this is my cam sensor here, and we can see that we've got this indexing position from the crank sensor, and we can see that just right before the middle of this ramp, I'm at top dead center at idle. Now we can see it snap. I snapped it, and we can see that we just barely moved a few degrees, and we moved just to the right of that position, but we're still way in front of the indexing. We're very close to the target. Now I want to show you what happened during decel. Do you see during decel, we were over here, and we moved all the way over here. Well, that's because the pressure waveform shifted. Nothing really shifted but the pressure. Always be aware that when I have a lack of pressure, such as a volume loss in the cylinder due to cam timing, due to a leak, due to high vacuum, such as in decel, or a valve not opening, these targets for top dead center are no longer true. As long as I have a stable idle or snap, I will have very close to TDC target. It will be very close. Good enough for diagnosing purposes. But if I have a volume loss, that no longer will be true. So be very aware of that. So we're going to do a cranking in cylinder waveform on this engine. So the first thing we want to do is we want to look up the pressure. We should have 135 on this engine. So we only have 130. We're a little low. I'm not going to really worry or freak out about that. I'm basically a mile high, which is going to give me less volume within the cylinder. So I'm going to have a little bit less pressure at my elevation. And I'm still close enough to the target to where I should fire the fuel. So we're in a range to where I'm going to be okay. Now, is it a little low? What am I looking at? Always remember, what is the symptom? What are you looking for? When you're doing this kind of work in the cylinder, you're always looking at why you're looking at it. Do you have a misfire? Do you think it's cam timing? Is there camshaft sensor codes? This type of thing. Everything that we do in a cylinder, always remember the symptom is what we're really looking for. What is the symptom? Why am I looking at this? And do I see anything? So my running idle compression, my exhaust is opening at 46 and my intake is closing at 54. So here we're at 42. We're really close to the target. And here we're at 39 and we're less. Now, the difference here is we're cranking. Now, remember when we were running, this was closer to being on target, and this was closer because we came way over here. So now we don't have the vacuum. Remember at idle, we had 15, 18 inches of mercury, Hg. So we have a lot of vacuum. Now we only have a couple of inches of vacuum, so we don't have that concentration of vacuum holding this all the way over until the valve closes. So during crank, we're going to come in a little bit from running. So when we're cranking the engine or idling the engine, we're going to be further over here because we have more pressure to hold that negative or flat until the piston is still coming up and I close the valve. So you're going to see a little bit of a difference between an idling engine and a cranking engine. And over here, we'll actually start to come a little bit different too. And both of these positions are caused because the volume concentrations that we have are less. I don't have as much tailpipe volume. I don't have as much intake volume. So we're going to have a little bit of change. So we're okay with that. Just be aware that that happens. Now, this is the intake and the exhaust pulls. So basically, the intake pulls and exhaust pushes are here. So now we're going to overlay these during my cranking. And I really like to look at my intake and exhaust during crank more than I like to look at it running. I'm going to look at both states, but a lot of times I can see this better. In a cranking engine, we've disabled the engine to where it's not firing the fuel. So now my exhaust will be all very even. So when I drop, this is more vacuum, and when I'm pushing, this is higher pressure. This is vacuum, this is pressure. So what I'm really interested in is looking at these points of reference to each other. And again, the same thing. This is less vacuum, this is more vacuum. This is less vacuum, this is more vacuum. This is less vacuum, this is more. Now let's take a look at how this might really work. So now we're going to look at this as my intake pulls and when the valve is opening. So this is my top dead center position here, and we can see where we drop pressure, and then the piston had to be moving to get it back up. And notice that I start to diminish my pull up here, and we come down, and the valve is actually opening about the 360 point, and I'm dropping. And then we're pulling up, and we're dropping. Now, when I make a transfer, this position right here of my transfer is very important. I transfer from one cylinder to the next. So this is one pull occurring, and then this is the next pull occurring. Now I come over to this cylinder. This is my peak to peak. I'm 360. So this is this cylinder's pull right here. So this part right here where I drop and then I pull up, I want to make sure that these upward movements are about even. I want to make sure that the width about halfway through this and the wave is made looks the same, and I've got about the same distance between all of these. So I'm looking to make sure these all look even, and most of all, I want these points at the bottom to be even. When you're looking at these vacuum pulls, just a little bit of difference to where this drops more than this does, it shows that I've got a leak. So when these start to drop down, it's indicative I've got a problem. And when these are higher, it's indicative that I don't. I had the vacuum remaining. Remember, this is more vacuum, this is less. If I drop down, that's even less. Well, why did I drop vacuum here and then it pulled back up and it maintained it? So these are what I'm looking for in this right here. And I'm looking at that during an idle. Now I'm going to zoom in on it. When I zoom in on it, I see more, I have more ability to see my points easier and to see how these guys are made. So all you got to do is use the zoom feature on your scope. If you don't have zoom features, you really need to get a modern scope, something that we can zoom in and we can look at these type of waveforms with. And again, we can see the top dead center position and we can see my low point. And then we're going to look at where the low point is, and we can see that my waveform, the compression waveform, started to drop here. That's where the valve started to actually open, and then we dropped down and we hit our transfer point. That's where we actually started to move volume to where we move volume and we can move this back up. And then we come to a transfer point, and then we move volume back up, and then we come to a transfer point. These transfer points need to be real even. If I start to get a drop, that's less vacuum, and that indicates a problem. So we need to be aware of that. So my exhaust pushes, I want to look at where this valve, do you see where this valve right here, I've got a marker through this, a line, and that's where we actually had a volume change right there. This is less pressure, this is more pressure, less pressure, more pressure, less pressure, more pressure. So we're pushing our cycles. So as the valve opens and we push our constituents or the exhaust gas out of the port into the exhaust, and then we have a change, or we're rotating what cylinder is doing the pushes. Now, in order to see what I want to do here is I want to see where this pocket down here, we just looked at that line and that was where we had our change. Now, do you see how this exhaust push, I'm pushing pressure, and right there, I had a drop of pressure. That's because that's where the valve moved. Now, remember when this was idling and I had latency to get that point of movement? It took time because I'm changing more volume in the exhaust. During crank, there's way less volume in the exhaust, so when I open the valve, I get this drop right away. Now, do you see how I came across sort of I'm pulling, or I'm pushing, I apologize. I'm pushing this out, and right here, I drop. That's where the valve actually opened. So now I can use these exhaust pushes to check my cam timing. I can also use the intake pulls. So I need to overlay these on my waveform so I can actually have another position to check cam timing. These are actually being changed by the valves opening and closing. That's what's moving these. So right here, I open that valve, and now this is dropping, and then we start to push again, and we come to right up here, and we open the valve, and we drop again. Well, this is going to line up with the exhaust pocket right here. Do you see where that exhaust pocket changed and I come up? That's what's happening right here. And so these waveforms that you see in your exhaust and on your intake, they're actually being caused by the valve opening. So now I can check when the valve's open. Another thing that I need to mention right now, always remember that any of this cam timing or anything you're looking, this is when volume changes occur. This is dynamic. This is when the valve actually changed a state and made a volume change, and the pressure followed the volume. We're always changing volume. So that makes the pressure follow the volume. What I want to tell you is that if I add something that looks like cam timing, that could also be a worn out lifter or rocker or cam or a tight valve or a loose valve. Those will all change the dynamic opening of the valve, which changes the pressure. So always think that 15 degrees per tooth, if I'm more than 15 degrees off, that's more like a tooth off. A valve, a tight valve usually creates about a 7-degree change. 7-8 degrees. So it won't quite be the 15. Now here on this engine, I can actually see that my ignition timing during crank is retarded. And on a lot of engines, they do retard them. Not all engines, but a lot of them, they retard it. And it will make it easier against the starter. You'll hardly ever see an engine that's in an idle position where it's running and it's idle and it will be retarded. There are some BMWs I've seen that have a retarded timing position, but almost all cars at idle will advance the timing somewhere between 7 and 20 degrees. And always remember that the timing is the first thing that we put in to correct idle problems. If the idle needs to be raised or lowered, remember when I had a distributor on a car and I advanced it, the idle went up, and when I retarded it, the idle went down. Well, the program, the first part of controlling an idle system is to throw timing in or out of it. If I need to idle higher, I throw timing in. And then when I get it there, I back it back out. Because I can move the timing really quickly within milliseconds, but to move a motor, an IAC motor, to move the throttle blade takes much longer. So the first thing to control idle or an anti-stalling device is I throw timing and I follow that up with a mechanical movement such as an IAC or a throttle valve. So most of the timing is going to be in an advanced state. On this engine, during cranking, it is retarded. And on some engines, running it is. But as I've said, running at idle, it's usually in advanced. And we're not running and we're not at idle on this waveform. This is a cranking position, and I'm just trying to show you that it's retarded here, and that's going to be okay. What I want to do is I want to put a leak. So here's my hose here coming out of the engine, and I'm going to put a leak over here. And this leak is going to lose the volume out of this system. So this is a closed system, and now I've allowed air to come out here. So that's what we're trying to do. We're just showing a leak. So the first thing I want to do is I want to look along here for high, low, highs. Do you see how even they are? If I have a valve that's seating and not seating, those are going to be, I'm going to have one high and one low. Now, 20 to 70, didn't I go 3 times? But isn't that relative? I should have somewhere 40 pounds of pressure here to 70 pounds is what I'm expecting. Now I have 20. Well, 20 is too low. That's not enough pressure. So that's not going to give me enough thermal energy. Now, once I snap this, notice that we didn't go up high enough either. We're only at 75 PSI. I had my 3 times, but 3 times doesn't mean anything. It's relative. I'm low here and I'm low here. And notice once I snapped, look at how slow my recovery. It's not recovering. This should come right back up. This should get in a decel and it should come back up to this position. Now, the other thing I want to look at is, do you see how I have some discrepancy over here? Look at how I can see these drops here. See these drops? We want to go ahead and we want to get in and we want to look at that. Okay, now the intake pull is way lower than the exhaust. Now, remember we said that this needed to be within 2 psi. Well, right here, if we measure the measurement from one cursor to another is given right here, that's over 2 pounds. So this is a problem. So we know that this should be within less than this. So this is showing that I have some type of leakage. Whether it's cam timing or a leak out the hole, that's a problem. So now I'm going to come to the top dead center mark and top dead center mark, and we're going to mark this guy out. And we're going to try to look at the cam timing. And we can see that we've got our marker here at about 30. And so that would indicate rule of thumb. I'm still close to my rule of thumb. I dropped here and I started to drop, but my whole drop did not happen before the 60 mark. I continue to drop all the way until I close that valve and I start to rise. Now that valve closing is at about 45. And again, that's showing my rule of thumb, which shows that my cam timing would be correct, right? But this is showing I've got a leak. So again, this whole drop should drop before 60 and I should have a flat plateau. In this one, I continue to pull out. Then when we go up to pressurize it, we're losing volume. So when we come back down, we have a discrepancy between these 2 points. So we lost so much volume that we can't make good pressure. We're only at 20 pounds. Now the difference between the pockets, again, we need to be less than 2 pounds. And really these usually are between less than a pound. By 2, we're really far out there. Usually these 2 pockets are very close. And we're just seeing that we have a problem on this. And again, we have an advanced timing position, but that's because we have a lack of volume in the cylinder. When we lose volume in the cylinder, our top dead center position moves, and we already know that now. So be careful when you're looking at top dead center that no longer is relative. We can't have big leaks and have a good TDC point. TDC will be good right up until about a 60 thousandths hole leak. More than 60 thousandths hole, and that's a pretty big hole, guys. When you're cranking the motor over with a 60, you can hear it every time it comes up on compression. That's not a small leak. It's a pretty good sized leak for a cylinder. So when we start to get a larger leak, TDC floats to the right and it no longer will be an accurate position. Again, we're moving to the right, and that shows that we're retarded or late in our timing. So now we want to look at these intake pulls up here. Here's my pulls, and we can see that our pull drops. So here, our transfer points here are okay. See how I dropped, and the very next pull, I built manifold vacuum, and then I built do you see how I'm building vacuum? Every pull I'm building vacuum, and then I drop the vacuum. And that's because when the piston is going down, it's not pulling the air out of the intake manifold. It's pulling the air through that leak. So this would be similar to what like rings would do, or some kind of a leak like that. So the idea is if I don't pull the volume from the intake manifold drops, and these transfer points show me. So I have more vacuum, and then I open this valve and I have less. And these 2 transfer points are lower, showing that this cylinder is leaking. Notice how I didn't pull up to as high a vacuum? Well, that's because to get that vacuum, I had to move the volume out of the induction system, out of the manifold. If that doesn't come out of the manifold, I don't have a pressure change. Pressure follows volume. So this shows I had a lack of volume coming out of that intake manifold. So where did it come from? Did it come by the rings? Did it come by some kind of a cracked head? Did it come from some kind of spark plug that's not tight, or you got to think about it's a sealed system. Where am I going to get that? An exhaust valve? Each one of these will give me a problem with the waveform. But one thing I want you to note is this waveform right here is this one. Notice this is my top dead center mark. This is my top dead center mark. It's dropped. Then it pulled up and I built more. It pulled up and I built more, and then it drops. This is a leak on this cylinder. That's how I can tell what cylinder is leaking. Now, when I snap the throttle, I drop down and we don't get very much pressure, and we have a pretty big drop down as the engine is increasing, because as it increases, the piston moves faster. Now what I want to show you is look at decel. Now what's going to be really important is to be able to figure out which one of these is compression and which one is exhaust. So let's put the ignition mark. Do you see how the compression tower is lower than the exhaust? So in this case, now if we're anywhere even close, we're lower or we're close, this should be at least 7 pounds or so higher than the exhaust during this decel. Well, when the compression ramp, and we know that that's top dead center, so that's compression, the exhaust is higher than what we have during decel is here. And again, this shows that I've got a leak. I've already covered other reasons that these could be low, but this is how we would utilize this in an engine we're actually working on. Now is what I want to look at is a leaking intake. So if the intake doesn't seal, this valve isn't sealing, and I've got a leak past that seal, how's that going to work? So we're going to first do a snap throttle in cylinder compression waveform, and this is an idle. So this is idle. I snapped the throttle and I came up. I had 40 pounds. I go to 140. Again, that's more than 3 times. That's always relative. But at 40 pounds, at least I'm 40 to 70, where I'm expecting 40 to 100, and that's good. Now, look at it. It took me longer to get my recovery, but I did recover okay, but I have a good long recovery, but not too bad, and I'm level again. So it did recover, and it recovered to a level position. I did have at least enough pressure during my snap, but really this snap, when you usually snap these, they're going to be well above 200 pounds. And at sea level, they'll be close to maybe 280, 300. Depends on the compression ratio and the engine and cam timing, and there's all kinds of other things that are important here. The intake manifold vacuum is running right here. When I snapped it, I can see the manifold drop, and then I can see it recover. Notice that my recovery is higher than where I was idling, and that should be because the engine is spinning faster now. So I'm looking for high-low highs through here, and I'm also looking for high-low highs up through here. This one high, this one low, this one high. So those are the type of things I'm looking at. The first thing when I get a waveform like this up. Now, one of the things that I want you to note right away, do you see how my intake pull? Do you see my exhaust pull is deeper than that intake pull? That exhaust pocket fell lower than that intake pull. Well, that's a problem. That's not going to work. We already know that if this exhaust pocket is lower than the intake, that we have a leak. So here we've got a line through it showing you where you can see that that exhaust pocket fell lower than the intake pull did. Well, if you've got anything like this, this is a leak. The only way we get this is leaking. There's no other way. When I came up on compression, I forced some of the volume out of the cylinder, and it's no longer there. And so when I returned to the same point that I sealed that system with over here, I sealed it, and now we drop lower than that seal point. I had to have lost volume for that to happen. So now we want to look at the pockets, and I want to show you. Do you see how this is warped? Do you see how this isn't smooth like a skateboard ramp? This should be totally smooth like a skateboard ramp. Do you see how I've warped right here and I got a sharp point here? Do you see how I've got a different, it's a light warp here, and then I've got a problem here? Now this is why you want to use a 300-pound pressure transducer for doing gasoline work. I have a smaller, thinner diaphragm. Now remember, we're at 0 here. We're only at a few PSI difference? Well, this is a 300-pound pressure transducer, so you've only got a few PSI here, and you're only seeing this really light PSI changes to get this warp. But this warp is indicative that I've got a valve seating issue. Now, a valve seating issue doesn't mean I have a misfire. Don't mistake what I said. That tells me that I have something wrong with the valve seating. And that's a different type of a problem. Am I looking for a misfire? What are my symptoms? Why am I looking at the waveforms? When I see lots of these, and every one of these is changing, cyclic variations. And remember, we had 40, 50 seconds of captures. When we start going through these and we start seeing that these are all warped and they're all different, every pocket looks different, the valve's not seating. Now we need to look at some other things to figure out if that's our problem or not. So here's a seating ramp. Do you see how smooth it is? See how it's like a skateboard ramp, and then I go up? See how smooth? Now, do you see all these little ripples here? Do you see that rippling? And do you see this edge? Mainly the edge up in here is warping, and then we've got these cuts. Well, this is not sealing. And we can also see that we've got a lower pull on the exhaust than what the intake is. But what we should have is it should be a little higher than the intake pull or equal to it, and it should be smooth. When we get these cuts and these ripples, again, this is indicative that I'm not sealing. This is a sealing issue in the valve. Now, according to SAE, valves only find a true seat, no leakage, 1 in 10 times. And that comes because we have this cut face at an angle, and we got this cut face, and when that valve comes down, it has a seal. But even a good valve is only truly seating every now and then. So now when you have one that doesn't seat very good, I've got a seating issue or some type of a burned valve, a burned seat, whatever, out of round valves. Now I have the pockets where the pockets start to change, and we get this kind of cutting, and they're doing it every cycle to cycle to cycle. When you're doing cycle to cycle to cycle, they should look like clones. They should look like these. They're really clean and they look just the same. When they start changing, then we start to be more worried about valve seating issues. Now this is my intake pull, and I can see that my intake pull dropped when I came up on compression. The green is my compression tower. This is when the piston is coming up and it's forcing the air back into the intake. So think about this. Am I going to have a problem during my intake pull? No. Where I'm going to have my problem is once I let the valve seat. During my intake pull, the valve is off of its seat. So I have a good pull and they're equal. And if I look across this distance here, they're equal. But when I start to come up on pressure, that pressure now is forced back into the intake, and it blows the intake down because I put volume from the cylinder back into the intake, and that means I lost pressure because I increased the volume. Remember, volume changes, pressure follows it. So I changed the volume. This is an intake valve not seating, and the intake is going down during my compression tower up. I force volume into the intake, which drops my pressure. Now we want to look at a cranking in cylinder waveform. Now right away, I can see I got a problem. Do you see these big drops here? See how big they are? Well, as soon as you see these exhausts really large like this, it's leaking. Next, I can look up here. I've only got 40 pounds. And I also got some high-low highs here. So these are higher and low. So I've got some problems. They're not even. And down here, these are really big. So this is a leak. Anytime the exhaust during cranking, if this exhaust pocket drops more than 2 psi, during cranking, this exhaust pocket can drop 2 psi less than the intake, and I'm okay. But when it starts to drop more than 3 pounds greater than the intake pull, it's leaking. And then the more it drops, the bigger the leak is indicated by that. What do I mean? So right here, I'm going to measure from the intake pocket to the exhaust pocket, and the difference is 5.5 psi. Well, during a cranking state, I should be within 3 psi. Really 2.5 is normal. 3 is getting on the far side, but I'm still okay. By 5.5, I've got a good leak. Anything more than 3 shows a leak. Notice the leaning tower. Do you see how close this side is? See how this is real close and this is wider? This is narrower, this is wider. Do you see how it looks like it's leaning? When I'm leaning, I have a mechanical failure shown. So here I've got a leaning tower, low pressure with a big deep pocket. I've got a leak. Now during cranking, do you see how this pole is going along and do you see how it drops? Do you see I started to compress and I dropped this down. So let's look at that better. I'm going to zoom in on it. So now I'm going to zoom in. Do you see how I have a pole and do you see this distance right here is about the same as this, is about the same as this? But do you see how this distance isn't the same? Because I started to make the pole, I closed the valve, and the piston started to come up on top dead center. And as soon as the piston starts to come up and compress that gas base that's in that cylinder, that is now forced back into the intake, and this forces the piston down. Or it forces the piston upward movement forces the volume from inside the cylinder back into the intake manifold, and it drops this. And in many times, if it's a big drop, you'll actually see it. This is my zero plane here. You'll see it go positive. It actually forces enough volume into the intake to make a positive pressure. But whenever you see a waveform like this, where I'm pulling and then it just drops during a compression, that cylinder that has the compression occurring is the one that's causing the drop. And that's an intake valve causing that problem. And again, we can count this out. This is cylinder 1, cylinder 1. This is cylinder 1. I had a good pull. Well, the intake valve is off of its seat. You're going to have a good pull. Now, we go to the next cylinder and immediately we start to drop it down because that valve did not seat, forcing that volume into the manifold, causing the drop. And again, you can see we want to look at the exhaust pushes here as well with this. And what we want to see right here is this is halfway, so this is the pull from this cylinder. Now, do you see I had more vacuum on this cylinder? Because when I blew this down, I lost vacuum, and then I had to build it up, and then I built it up, and now I have the most vacuum. Now, when I have the most vacuum in that cylinder, I have the most vacuum, so when I open the valve, I have more vacuum. Notice how this intake, this exhaust, had a higher pull right here? Do you see, if we go halfway through, this is the exhaust push from this cylinder. This is the intake pull from this cylinder. So do you see how low this exhaust push is right here? Well, that's because I have more vacuum on that cylinder, so I had a deeper pull over here on that cylinder. So here we've got them marked out. So we've marked out the pulls. So this is the pull from 1. And this is the push from 1. Do you see as soon as I opened the exhaust valve here, I had more vacuum in that cylinder, and that causes a bigger drop. So this drop is showing me how much vacuum or pressure is in the cylinder. If I don't have any vacuum, this is going to come up higher. It's not going to go as low. These should be very equal. And you can see right here where this one's not. And that's because the vacuum state inside the cylinder is changing. Remember, this is the push, this is more pressure, and this is a vacuum state. And remember, we have a vacuum state, as we've already talked about, when we don't fire fuel in the cylinder. Now we want to look at the exhaust. When the exhaust valve doesn't seat, what do we have? So basically, we want to do the same snap throttle where we're idling and we snap. So right away, I've got 36 pounds. That seems low to me. I want 40. 40 to 70 is more normal. Doesn't mean that that's a miss, but that means I'm not comfortable with it. Maybe that's normal for the engine, but normally I want a little more pressure than that. And then I went 3 times that. So I went 36 to 142. Again, it's relative. So I'm looking for high-low highs, and I'm also looking for high-low highs up in here. What do we see? And then we want to come down in the vacuum, and then I want to see my might pull up. Well, over here we overshot because the engine is letting more air in there to try to stabilize it. This is more air right here. This is my stable idle. I snapped it. Now my throttle plate or my IAC motor opened up more and it let more air in there trying to stabilize my target RPM. Notice that when I stabilized my air, notice my intake pull dropped. Do you see how they're inverse? I lost vacuum and I had more pressure because the vacuum means that I didn't let as much air in there. Less vacuum is more air where I get more pressure. That's what that's showing me. So now when we go in here and we blow this up, we can see that at least this is about even now. So I'm okay with that. But do you see how this pocket's all funky? Do you see how this is curved? And it's curved. And notice these notches. And notice this cut right here. That cut's not here. Notice how it's all rounded. I have a cut right here. And here I've got some kind of rounding. And here I've got a front notch. They're all different. So something doesn't look right here. So let's look at this. So here, when we mark this, look at how the pocket comes way over here. Do you see how I don't have a clear definition? Where's my definition supposed to be? Well, rule of thumb is 30 to 50 degrees, maybe to 60. This is out towards the 60, but this isn't like I'm curving down and I jump up. Notice how the curve is coming from the intake side all the way down, and this is a really not uniform pocket. When we get pockets like this, or the pocket is totally rounded, it's telling me the exhaust valve is not seating. So this is a seating issue with the exhaust. But I can look right here, and at least I'm still within my specification, about halfway to the top in the ramp for my cam timing. So my cam timing looks roughly right. And if I had a misfiring cylinder, I want to be in the misfiring cylinder to find my pressure loss. But maybe I would take one of the other spark plugs out and I would do a good cylinder to compare it so I can start to understand what the differences are. Again, we have this ripple. That's normal because the exhaust valve is open and I'm in pressure communication with the exhaust and I have pressure pulsations in there. We have multiple cylinders pushing pressure. We have hot turbulent gases burning. We have a muffler that's creating a pressure differential, bouncing waves. So this is all normal. And then we opened our valve here and we had a drop, and we dropped before our target of 60 when my halfway point roughly. If I had cam phasing, if I didn't have cam phasing, and we'd be at 20, we're still within our target on that ramp. And we'd come over here and we'd see we're roughly within the target again. We're about the edge of it where we would be at the 60 to 40. Most of these I like seeing at about 50, 60, but 30 on some engines is okay. Remember, these are always relative. What are we looking for? Why are we looking? We have a little bit of a leaning ramp. This is a little wider than this, but we're still probably within our 20-degree target. But you can definitely see the ramp is starting to lean, and we're low on our pressure. But this definitely shows I got a problem with the exhaust pocket. Now I want to show you, this is a rounded pocket. This valve flat didn't seal. Do you see how there's no point of definition? I can't see a pressure change. It's just all round. Well, that valve is not seating, and that's a problem. Now this is a good pocket. Do you see how I come down to a point and I drift this point into this point? And I have a clear point of definition. That's what I'm looking for. I want a point where I can see it changed. It changes its pressure. Up here, I don't have that. Where's my point? There's really not one. It's just all round. Well, when you got all round exhaust pockets, it's showing me I've got a valve that didn't seat. And here's a bad valve to where the valve's not seating. Do you see again? I don't have this nice curve down and a quick rise. Notice how I've got something ununiformed here. This is a bad seating pocket right there. So now I want to look at the intake pull. This is my intake pulls up here. We want to see what they're doing. And right here, I had a drop. My transfer point, when I first opened it, I had higher pressure, right? This is more vacuum. This is less vacuum. I pulled up, I had more vacuum. I pulled up, I had more vacuum. I pulled up, I opened that valve, and bam, it dropped. But it didn't drop all the way, did it? But as I'm pulling the air, now the exhaust valve is not seating. Since the exhaust valve is not seating, it is pulling the air in through the exhaust. Since the air is coming from the exhaust, I did not pull the air out of the intake. So the volume's not coming from the intake manifold. Part of it's coming from the intake. Part of it's coming from the exhaust. So the pull isn't as high. Notice this transfer point, the pull up. Notice this is to the pull up. I have more pressure differential change. Notice this one where I opened the valve and it dropped and then it didn't have the pull. It's not as high. Well, that's because part of this air is coming from somewhere else. It could be coming from the rings. It could be coming from the exhaust or some other, a crack or something. But, usually it's going to be the rings or the valves. So that's what I'm looking at. Well, where did this come from? Well, I can look at the exhaust pocket as we just saw, and the exhaust isn't seating. So now I know this air is coming from the exhaust, and now I drop way down because I've lost manifold vacuum here. I didn't pull back up to have good vacuum up in here. I didn't have as much volume taken out of the manifold as I did from the exhaust. So I'm pulling air as the piston went down from the exhaust and the manifold. I lost pressure. So as soon as this valve opens, it flat drops further. But this isn't the cylinder that's leaking over here. It's this one that's leaking. And this is just showing that I didn't make vacuum during the number 1 cylinder pull. Remember, halfway, this is my target, halfway, 1 revolution. To the right is my intake pull. This is cylinder 1, so now this is cylinder 1's intake pull. It didn't pull up. I get a further drop on 3, but 3 is not the problem. 1 is the problem. So you can clearly see from this point to this point, it just didn't pull up as much. Now we open the valve and we had less vacuum in the intake, so we drop further when we did open the valve. Now we pull up. Do you see as soon as we got rid of this valve, this cylinder, we closed that intake? Notice that we lost the pressure during the intake. The intake valve opened, the piston went down, air came from the intake, but air also had to come from somewhere else, and I diminished the volume pull. So the air is coming from an exhaust valve or maybe the crack case by the rings. Now we come down and we close that valve, so now our vacuum can build again. And this point right here, this is 3 here, this is 3 here. Now I pull more vacuum, I pull more vacuum, I pull more vacuum, I open this, I drop. Now I don't make much vacuum because during this pull, air came in from somewhere else. When I open this valve, it flat drops. Now you know it's the cylinder because I gained pressure. I have a good pressure differential from this point to this point. Do you see that? I didn't on this one. So 1 is my leak. And again, I can see that in the exhaust pocket as we've already looked at. I want to show you a volume test. So if I take this unit right here, and I'm going to make a sealed system, and we're going to see how much this has. I'm going to put a vacuum on it, and I want to show you how this drops. So basically, the reservoir holds 0.85 liters. Now, the volume in an intake plenum generally is 6 times the volume of 1 cylinder, or about 3 liters. You don't usually see larger manifolds than 3 liters, because we have latency. The bigger the manifold, the bigger the accumulator. And we want good response, so we want a smaller intake, so when we open the throttle, we get a good inrush and we get air and it changes quickly. In race engines, you can have 5-6 liter engines, liters on the intake manifold. So 6 liters, double what's normal on a car, because I'm not looking for throttle response. And it doesn't really matter. I'm looking for the overall gain at the top end. But for most driving cars, street type cars, you're going to have about 3 liters or less. So in this case, I'm showing you that this is way less than the intake is. This is not even 1 liter. This is 3 liters. So what I want to do is this orifice in my cylinder is 100 thousandths. So that's a pretty big leak. I mean, 100 thousandths would be part of a valve missing or a really burned seat somehow. So that's my solenoid hole that we're gonna drain out. Now my solenoid is commanded on and it's commanded off, and I turned it on for 35 milliseconds. So this would be the same time that a stroke occurred running at 850 RPM. So 35 milliseconds by 4 strokes, that's 140, are about 850 RPM. So I turn this on for the time the valve would basically be open. Now I turned the solenoid on, and it took a latency for it to open to where I affected my pressure. Look at the drop, and then the drop climbs right back almost to where it was. It's a little lower, but do you see how when I open the leak, I get this drop and then it comes back up? Well, the drop, depending on how big it is, will tell me how big the leak is, but it also has an effect of how big my reservoir is. But you can sort of start to see when we're looking at those intake pulls, we get that drop and then it pulls back up and it drops and it pulls back up. Well, that's what this is showing me. So now we want to look at this for the exhaust pushes. So here we've got this, and we can see that this is where the exhaust had this, and we came up, we opened, we have a little latency. We can see the one that had the misfire right here. Notice that we had a bigger drop, fast overrise, then it overshot. Notice these are all lower with an overshoot. So this is the cylinder that's missing, which would be 1 halfway through the fire cycle. That's 1 revolution. That's the center point. Go back to the left. That's the cylinder I'm using. Whether this was a in-cylinder pressure waveform or I was using a ignition coil from a cylinder, I can figure out the pressure loss in the exhaust will tell me what cylinder is missing, just like here. And so basically I can see that I opened the valve and I had this over here for this, and we have some latency. Again, we have a pull and a pull, and once the motor's running, the exhaust is going to be far more unstable. It's going to be harder to see stuff because we have a running dynamic engine. With it cranking, it's going to be a little bit different waveform. So now we can see my big pull, my big drop, my pull on the exhaust pocket. We have a low cylinder, high, low, high right there. And we have low pressure, big pockets. And I can see that I have some rhythm in this intake pull right here. And so now we want to look at that. So now is what we're going to see is, one, we have a leaning tower. And that leaning tower is always a mechanical failure. We have a pocket that's all rounded, which tells me that the exhaust did not seat. So the exhaust is having a problem. So now we want to look at these intake and exhaust pushes. So here's my intake and exhaust pushes. Notice 1, this is cylinder 1. So we go halfway, and to the right is my intake pull. Notice that I had a pull, my transfer point, pull. Notice it's pretty even. Pull, it's pretty even. I drop. Now, that's not as wide as this one. It's a little less, and it didn't come up as high. So from my transfer point to here, transfer point to here, transfer point to here. Again, this is a cranking waveform. And once I regenerated and I closed that valve, notice that I had a pull here, and I pulled up and up, up and up and up until I opened this valve and I lost my vacuum. Notice the transfer point is lower, and this one's even lower than this, as we've already established why that occurs. Notice that this one is lower than this. Once I close that valve, I can make vacuum in the intake, and then I climb vacuum. It pulls. And again, this is cranking where I don't make much vacuum. And again, this is why we want the throttle plate closed, so we can get these kind of waveforms. If the throttle plate, if you're holding it wide open, you don't do that. You won't have a good waveform made for you. Now, again, when we look at the exhaust pushes, do you see one? Do you see how small this pocket is right here? Well, do you see how I had less vacuum? This is less vacuum right here. Well, if I measure from here to here, I have a lot more vacuum. When I measure from here to here, I had less vacuum. So when I have less vacuum in that cylinder and I open the exhaust, I have less inrush of air because I have less pressure differential. Do you see how small that is? Do you see how these are all bigger and then this is small? It's because I don't have the vacuum, and when the pressure in the cylinder is there, so when I open the valve, that's what's creating that inrush back in through the tailpipe, but I just don't have that right here. So I just don't have as much. And again, we can see where we open the valve, we can see this exhaust pocket right here. We open the valve up and it drops. But we don't have the pressure change. As we can see, these are all more even. This is higher, and this is just indicative of this problem right here where I have low vacuum. We want to look at an exhaust restriction where if we're pushing the exhaust base out, I've got back pressure coming back into the cylinder. So we want to do a snap test one more time. So now we're doing this test and we're at idle here. And notice we have this is created by the vacuum. We've been over this. This exhaust pocket right here and this whole exhaust plateau is caused by vacuum. This line is atmospheric pressure. Now notice as soon as I snap the throttle, I start to lose the vacuum right here. But do you see how I got that plateau back in here? And you see how the plateau is getting bigger and bigger and bigger and bigger as the engine races up. This is getting bigger. Do you see that that is a pressure plateau? This is a vacuum plateau. So this exhaust plateau at idle is by vacuum. This exhaust plateau right here is by pressure. I'm pushing against a catalyst that's plugged. So in this engine, I have a bad catalyst, and that's giving me more and more pressure, as we can see right here. Now, the way I want to measure this is I want to put a cursor peak to peak, and then I want to snap the throttle and I want to let it rev. So I want to go back and I want to do these over here. Let it get some RPM to where we got more pressure coming up, and I want to measure these bigger ones over here. Don't measure the first one. Measure some over in here. Once it starts to rev, you'll be more accurate. I'm going to put a cursor peak to peak. I'm going to mark it. My marker comes up. I want to measure 30 to 60 degrees. This is bottom dead center. So I want to go to 30 to 60 degrees. And I only want to go to 30 to 60 degrees. If this continues to rise up over here, I'm not measuring that for exhaust back pressure. I'll explain this momentarily. I want to measure from my exhaust pocket to whatever the peak pressure is, only between 30 and 60. So from here, the lowest point right here to the highest point, only between 30 and 60. That's where these are. Well, I have 22 pounds of back pressure right here. So that's telling me I have too much pressure. Anything more than 8 psi is a restriction. Most cars you're going to snap will be 4 to 6 psi. 8 is starting to get restricted. By 10, you will have a drivability problem. By 22 pounds, you have a problem, and you'll feel it. The car will nose over at higher RPM. As the volume increases, the pressure increases. As the engine starts to rev higher and I'm pushing more volume out, I'll have higher pressures created during that back pressure situation. So this is my pressure from this point to this point. That's 22 pounds. So if this pocket was low and it came up at the 360 point and it's real high at 360, well, the piston was a bottom dead and it's coming up to top dead. That's telling me I have a scavenge problem. That's different than a plugged exhaust. That's different than a catalyst that's plugged. This has something to do where it's up here with cam timing or a partially restricted port. Those are different problems. Anything that has a high pressure at the center, I can't scavenge. I can't push the exhaust out. So the closer the piston gets to the head, the more volume is still in the cylinder. Remember, the valve was supposed to be open and it was supposed to push out all of that volume. If it can't push it out, it starts to make pressure. If the exhaust valve doesn't open, I'll have a peak here, and this will be totally rounded. It rounds all the way and comes way back up to almost the same peak or to the same peak. And then it drops down, and you'll get the intake valve open, and we'll get the pop back out the intake from a problem like that. But just be aware, anything that has a rise at the 360 point, that has to do with a scavenge problem, cam timing, a flat cam lobe, worn lifters, rockers, a partially plugged exhaust, something like that. That's more what I'm looking at that type of problem. When I got a plugged cat, you measure only between 30 and 60 from the lowest pocket here to the top pocket here. Anything more than 8 pounds, you've got some kind of restriction. By 10, you have a drivability problem. I thank each and every one of you for your time. As I get older, the one thing I understand is money comes and goes. You know, it's no big deal, but my time slips through my fingers like sand. And once it goes through my fingers, it will never, ever come back. It's gone. So the most important and valuable thing that I possess is my time. And I thank each and every one of you for spending the most important asset that you own, and that's your time. So now I am ready to take your questions, and you guys have an absolute outstanding week in your service bays. Hopefully this helps you diagnose these vehicles.